Taylor's theorem is a theorem which is used extensively both in calculus, applied mathematics, and engineering applications. In a way, it's meant to be a generalization of the mean value theorem to higher order derivatives. We can apply the differentiating rules repeatedly. When I say apply them repeatedly, I mean apply them repeatedly to a function f in order to obtain the higher order derivatives. So we're talking about f prime prime, which is really just the derivative of the derivative, which we used to call just the derivative, but now that we have the ability to differentiate twice, we're going to start calling it the first derivative, in contrast with the second. F prime 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 would be f prime prime differentiated, the same as f prime prime prime. You get the idea. You remember this from calculus. The concept has not changed. Now let's see, you have a function f which has an nth derivative at the point x0, x0. The nth Taylor polynomial of f of x0 is going to be, I'll write this on the other slide just to have a bit more space, Pn at x0, and then we don't always specify the f if the context makes it clear what function we're talking about, but we might as well put it in there at least first time. That would be a constant term, the value of the function at x0 divided by 0 factorial times x minus x0 to the power 0. Now the clever student here will remember that 0 factorial is just 1, and x minus x0, assuming that x is not equal to x0, that would be something which is not 0 to the 0, which is also 1, so this is just f x0, the value of the function at the point x0. But we're going to write it like this in red because it does indicate what the pattern is for higher order terms. Then we'll compute the value of the first derivative at x0 divided by 1 factorial times x minus x0 to the power 1 plus f prime prime x0 divided by 2 factorial x minus x0 squared plus f prime prime prime, third derivative at x0 divided by 3 factorial x minus x0 to the power 3, and you're going to go all the way to the final term, which is the nth derivative of the function f at x0 divided by n factorial times x minus x0 to the power n. Implicit here, if we say that the function has an nth derivative at a specific point, is that it has all of the lower order derivatives at that point as well. So how is this useful? Well, there's a very important theorem. This is one of the named theorems. I'm actually also going to provide it to you in uppercase letters, just so you understand the importance of this theorem. N is an integer. F is a function from the interval AB into the real numbers. We have the f prime, f prime prime, f prime prime prime, all the way up to the nth derivative, continuous on the interval AB, and the next derivative exists on the open interval AB. Of course, when I say that these derivatives are continuous on the closed interval AB, I'm also saying that they exist on the interval. For a general function, even if the function is continuous, there are no reason to suspect that the derivative would be continuous. So asking for these derivatives to be continuous is actually a pretty strong requirement. It's a strong assumption. If x0 is some point in the interval AB, which I might denote by I to avoid having to write too much, then for every x in the interval, there's got to be some point C, which will depend on your choice of x, between x and x0 such that f at x is equal to p and x sub f, the nth Taylor polynomial of the function f at x, plus a remainder term. It's the n plus 1th derivative evaluated at the point c, divided by n plus 1 factorial times x minus x0 n plus 1. This one has a slightly different form. In the formula for the Taylor polynomial, we evaluated the derivatives at x0, point of interest here. And you know, one of the things I just realized, I wrote Pn at x0, but this isn't Pn at x0. The Taylor polynomial is a polynomial at x. Right? So this whole expression here, x0 is a constant. It is known, it is given, the variable is x. Okay, so what is it that we need to prove here? We need to prove that the function is the Taylor polynomial plus some correction term times x minus x0 over n plus 1. This is meant to be true for every x at I. Now, note though that for every x at I, you will get a different c. Let me just write this here as cx, just so we recognize or remember that the c will not be the same for every x. How would we go about proving? I'm going to give you a proof here which reads as though this is the most natural thing you could think of doing, but I want you to be aware that this is a proof that required a fair amount of polishing to make it pretty and logical. We're trying to show something is true for every x in I. Let's pick an x in I. We also have an x0. That's part of the statement of the problem. If it turns out that x0 is smaller than x, this situation here, then we are going to set a new interval j to be the interval x0 x. Should we call this jx? But I might drop this a while. If, on the other hand, x0 is greater than x, the interval jx will be x0. What happens if x is equal to x0? Well, if x is equal to x0, there's nothing between x and x0 except x, which is also equal to x0, and that's going to give us a different expression here, right? This whole term is always going to be 0. So we're going to have to take a look at that perhaps differently later. Now let's define a function capital F. We define it from the interval jx is a set of real numbers as follows. For every t in that interval, the outcome, the output of the function capital F will be f at x. We know what that is because x is given to us. We picked it to start with. Minus f at t minus f prime at t times minus t minus so forth until we get to the nth derivative at t divided by n factorial x minus t to the n. And we know that this exists because all of the derivatives are known to exist on the interval ab. And we've picked our x and our x0 by assumption so that jx is actually contained in the interval ab. So this function is well defined. What is useful about it? Well, its derivative is fairly easy to compute. F at x, when we differentiate with respect to t, that disappears. And then we're left with the derivative of minus ft, so that's minus f prime t. And here what we have is minus f prime prime t times x minus t. I've differentiated the first term of the product plus f prime at t times the derivative of x minus t is minus 1. I'll do the other one as well just to say that we do have it, so that's not written explicitly here, but you can figure out what it would be. F prime prime at t divided by 2 factorial times x minus t squared. So that gives us the derivative of the first term, f prime 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 divided by 2 factorial times x minus t squared plus the derivative of x minus 2 squared. Bring down the exponent, use the chain rule, multiply by minus 1 times the original or the initial term, f prime prime divided by 2 factorial, and so forth until we get the very last term, the nth plus 1th derivative at t divided by n factorial times x minus t to the n plus f nth derivative at t x minus t n minus 1 times n minus 1 times n times. Now some of the terms are going to cancel out, right? This 2 and this minus and this 2 factorial cancel out. In fact, what I should really tell you is that 2 and 2 factorial leaves 1 factorial. Not even true, sorry. They'll all sort of cancel out. Here we have n divided by n factorial. So we're left with n minus 1 factorial. If you look at the terms, you're going to have a telescoping sum. Minus f prime at t minus f prime at t. These terms cancel. And then I have minus f prime prime at t times x minus t minus so plus f prime prime at t times x minus t. Well, these terms cancel. And all of the terms successively cancel out until we are left with. I told you it canceled out. This one doesn't actually cancel out, my bad. So all of the terms cancel out except for this term right here. Take the time to double check that you understand that the derivative of this function f is indeed minus the n plus 1th derivative of f at t divided by n factorial times x minus t to the power n, because we have here a telescoping sum when we compute the derivative. Now we know that the function f is continuous because it is a sum of continuous functions. I didn't specify in the statement of the theorem that f had to be continuous, but if you think about it, f prime could not be continuous if the function f itself was not continuous. Well, even though it wasn't explicitly stated here, it was implied by this strong assumption. And f is continuous on its interval here, jx. These derivatives are continuous on jx because jx is contained in I, and derivatives are continuous on the full interval I. They're also continuous on a subset. So now we build a new function. Function capital G. It goes again from jx to r. It is defined by g at t is big F at t minus the following expression. x0 is given. It's one of the endpoints of the interval. X is also given. It's the other endpoint of the interval. And t is our variable. What do we have? I compute g at x0. I'm going to replace t by x0 throughout. I have f x0 minus x minus x0 over x minus x0 to the power n plus 1 times f at x0. This equal to 1. F at x0 minus f at x0 equal to 0. On the other hand, g at x would be f at x minus x divided by x minus x0 to the power n plus 1 times f at x0. This becomes 0 because x minus x is 0. It's just capital F at x. And we know what the definition of capital F at x would be. Use this definition. Okay. F at x minus f prime at x times x minus x. So all of these little terms here will have minus these will have x minus x. We compute here. This cancels out to 0. This is 0, 0, 0. They're all 0. You get 0. G continuous on jx. Either x 0 here. Look like this. T function is 0 at the endpoints. So it satisfies hypotheses Paul's theorem. Since the derivative of this function exists, that is going to be the derivative capital F plus n plus 1 x minus x0 times x minus t x minus x0 the nth power 0 using the chain rule here, the original term So since this derivative exists on the interval jx, we know that there exists some value c, which would be in jx, such that g prime c equals 0. That's the conclusion of Roll's theorem, which is basically saying we have a continuous function on an interval, and it is 0 at the end point. There's going to be at least one point in there where the slope is horizontal, where the derivative is 0. Now there's more than one in this drawing. We don't know what g looks like for real because we don't have an actual function f. We haven't specified what n was. We didn't pick an x0 and x. All of this is up in the air in terms of having a specific example to work with. But what we do know is that there is a point in there where the slope is equal to 0. Where the slope of what? The slope of g. Well, what does that mean? Remember what g is as a function. This function right here is defined with the help of f. In particular, what we get out of this, we evaluate the n plus 1 derivative at c divided by n times x minus c to the nth power. This is going to be the same thing as n plus 1 times x minus c to the nth power divided by x minus x naught, the n plus 1 power times function f. Now, where do I get this from? It comes from here. G prime at c is 0, meaning that f prime at c is equal to this expression here. What you get out of this, that f x naught, this term here, you multiply, divide all the terms. That's going to be the n plus 1th derivative of f evaluated at c divided by n factorial, this thing here, divided by n plus 1 here, times x minus x0 to the power plus 1. One goes here, and then the x minus c and the x minus c will cancel one another. Solve for f x naught. Now, one thing I should mention is that I did do a little computation error. The derivative of g was not f prime plus, it was f prime minus. Now you see what's happening. Because I know what it is that I'm looking for, because I've worked out the proof previously, when I get to this point here, if there had been a plus, this wouldn't have made sense. Now I knew what I was trying to get. I was able to sort of force it here, but there was a nagging doubt in the back of my mind. I kept on seeing this plus right. It had to be a minus. I made a silly mistake, and I left it in, and I made it to catch it time. My knowledge of how the proof is supposed to develop allows me to say, oh, hang on, I did make it. But if you were just writing this down without having worked it out first, that probably would not be something that would have registered for it, right? We wrote g here, a minus sign. Had to carry over when you compute the root. All right, so then what's happened? What have we found? What can we say about little f? Well, let's look at the definition of big F at x. Big F is this thing. So if I evaluate it at x naught, get this expression here, which is by direct construction the same thing as f at x naught, f at x minus f at x naught minus f prime at x naught times x minus x naught minus all the way to the nth derivative. And that's the true value from a few slides ago. So you again, to be double sure, it's this thing where I replace my t by x naught throughout. So that's the direct value of f at x naught, and all of the other work that I've done has shown me that, well, f at x naught is also equal to this quantity here. So now I'm gonna, one here doesn't have an x naught, I'm gonna solve for f at x. So basically take all of this, send it over to the other side. N plus 1 times n factorial, that's just n plus 1 factorial, times x minus x0 to the n point. This first bit is the Taylor polynomial, this bit here, the remainder. That ends the proof. This is a wild ride of a proof. I can't see how anybody would naturally, without having worked this out first, and worked out backwards, how you could have possibly proven this directly, pen to paper. Okay? Like coming up with this function. You have to work from this back. This is often how you do things. This is a proof that I want you to take the time to rewrite on your own, in your own notes, in your own language, in your own hand, so that you understand each of the steps. Now, I made a number of goofs along the way, and I'm not going to try to pretend that I did these goofs on purpose. I did. It's late at night, I'm exhausted, not thinking very well right now. But it's important for you to figure out, write down this proof without the proof. This proof has the flavor of an actual analytical proof, and it uses some interesting results along the way.